Thank you very much for the invitation. I'm going to present this work. So it's large language models playing games. And the table of contents is the following. So first I'm going to give a small introduction to large language models, then an introduction to mixed strategy Nash equilibrium games. Then it's going to be the main section, which is LLMs playing these games, and then some conclusions. So first, what are large language models? So unless you have been underground for a few months, you should know more or less what are language models. But let's start from the basics. So what is completion? So usually large language models, what they're good at, it's completing sentences. So for example, if I start with 1, 2, 3, what you will expect to get, it's 4, 5, 6, 7, 8, 9, 10. And you can get this programmatically through OpenAI. In particular here, I'm not using OpenAI, I'm using a local model, which means that these results are reproducible. You can play it with them in your computer, and every time you will play with them, it will be the same because it's not OpenAI, which is constantly changing models. Okay, so you can, here I'm using Mistral model, 7 billion, 16 floating points, and here you get, okay, the response that you expect. Now, what most people see is not this. What most people see is chat. So it's ChatGPT. So what most people see is they ask a prompt. They ask, for example, what's the capital of France? And they get an answer. The capital of France is Paris. But what they don't see is that this, you can do it programmatically as well, which is you have a visible user prompt, which is what is capital of France. And this gets translated. You can send it through messages, and you go to another API, which is called the API of chat. And then you get the answer, which is the capital of France is Paris, as a role assistant. But this chat, these messages, and this chat completion is fake. You don't need it. Because in reality, if you look at, here I'm using just an application of I take the original visible user prompt, and this is what the large language model sees. So what the large language model sees, it sees this, and then he knows how to follow, and it knows that the way to follow this is the capital of France is Paris. So here you can see there are some special tokens. So this S here in particular is the beginning of text, of beginning of session. Here is the user starting to talk. Here is the user ending to talk. And to be honest, this applied chat template has a problem. So usually you should add a space here. If you read the model documentation. So first of all, there are problems if you just take whatever you take and you don't look into it. Okay, so this is what most people see in chat, but there is something very special also, which is function calling, and this will be important in the talk, which is the possibility to call functions. So a large language model has the possibility to call function. This is now open to everyone. For people who pay ChatGPT, you could have played this a few months ago, but this is open now to everyone. You can ask a question like, what's 1, 2, 3, 4, 5 times 5, 3, 5, 4, 3, 2, 1? If you ask the large language models like this natively, okay, perhaps this one he knows, but if you start asking 6-digit question, it will fail. And this is well known. And this is not, I'm not saying anything. This is well known, and there are people trying to fine-tune models to make it do arithmetic operations. But in reality, one thing that you can do is just simply make the model call a function. So in this case, I'm putting use Python, and the model knows that he should use Python, and he just uses a multiplication between two numbers, and he can get the result. And then you get a nice result here, 1, 2, 3, 4, 5 times and you get the correct answer. So this will be important. And how do you do that programmatically? So programmatically, this is the visible user prompt. And in reality, what you should do, I mean, you can either describe a Python shell, or here I'm describing a multiply function. And you describe this function, what it needs to do, some description of the parameter it needs, and what are the required parameters. And you get, finally, this kind of prompt. So this is prompt, it has some special tokens. So you have the S at the beginning, which is it's indicating a beginning of session. You have this, which is the beginning of a user. You have this, which is the end of a user, but you have some special tokens. And these special tokens are not available to all models. In particular, this model has it, which is the capability of calling functions. And for calling a function, you need to provide this saying what are the two tools available or the available functions with this token. And you can show it between these two, and you can put multiple functions. Here I'm just putting one function, which is multiplication, but you can put several, and the model normally should classify which one to call. So, and then I'm forcing the model to call that function. So this is something most people do not do, but here you can force the model to call a function, which means I don't need to ask it, please don't be too verbose, please shut up after you have done the calculation. No, here you just explicitly tell the model, call a function. So you can guide it with this way. And here you get, so function calling is in reality, what the model tells you is what you need to call and what are the parameters, how to call it. So in this case, you can run this function, and this is what ChatGPT does in particular. But this is in reality function calling, and people think that the model is calling function because this is the image that the word provide, but in reality is just providing this. And then it's up to you to run the function. Okay. And usually models, large language models are not perfect, so you can do some regex to clean the answers. In this case, the answer was quite clean, so you don't need to do anything, but you need to know that there exists some ways to clean the outputs. Now, most people do not define these functions like all this JSON that I showed. Most people do it this way, which is more programmatically clean, I guess. You define a Pydantic object and you the Pydantic class, sorry, and you define in this way with some description. And then there are some tools, for example, in this case, LangChain, but you can use Instructor or others, which will provide this translation from this function to JSON with these characteristics. This is just a help for the coder, but in reality, you can just take this string and you don't need to do any of this. I'm just explaining it so that you know that it's easier to define functions than what I showed at the beginning. And in particular, one function that you can take is the Python. This is the one that I showed as ChatGPT was using, which you can define a Python shell, et cetera, with some description. This description was written by LangChain, but you can write your own. And perhaps it will be better. Perhaps it will be worse, but so this is just to say you can do it yourself also. Okay, so you get, going back to our problem, we get a visible prompt, and you get some, so this will be the prompt that the model will see, and then he will reply with the arguments, which are this. And in that case, you can just clean it, and you get the final result, which was the same that the model provided in the Python code, in the Python case. I mean ChatGPT. So you can do all of this programmatically. No need to pass to this user interface. No need to pay 20 euro per month, but perhaps it's convenient to pay this 20 euro per month. Anyway. Okay, so this was the introduction to large language models. And now I'm going to introduce mixed strategy Nash equilibrium games, which is a phrase that I invented because in reality it doesn't exist in the literature. No, I mean, it exists pure. Okay, I'm going to explain. So I'm going to explain with one simple game, which is matching pennies. In the paper, I also talk about rock, paper, scissors, but matching pennies is a very classic game. So it's a game in which there are two players. It's a one-shot game. Each player has two possible actions. You either play heads or tails. Both players will reveal their answers simultaneously. If both choices match, then player one wins. If the choices do not match, player two wins. So the payoff metric is like this. So if both of them play heads, player one gets 1, and player two get -1. If both of them play tails, the same. And if they play opposite, player one loses and player two wins. Okay. So is the game clear? Because I'm going to elaborate on this game. Yeah. Okay, and you can think of plenty of examples. Here I'm just giving one just to motivate if you need to. Which is Alice and Bob need to communicate sensitive information securely over a network. It has only 2 distinct communication channels. Let's call them heads and tails. And you have Eve, which is an eavesdropper, and he aims to intercept the message. And Eve has the capability to spy on only one of these channels. Okay, this is just one application, but you are smart, so you can think of 100 applications. But this game has a very well-known Nash equilibrium. So first of all, you need to notice that there is no pure strategy Nash equilibrium, which means I cannot take always the same action. I mean, if the other person know that I will play heads all the time, then he will always play whatever makes him win. So, and similarly for tails. So the best strategy, or in this case, it coincides with the Nash, will be to play 50%, 50% chance, 50% chance between these two options. Okay, and you can see it because there is no once you start here, there is no incentive to deviate. Okay, so you have you can modify this game. You can modify the matching pennies game with this payoff. And here, for example, I modify the payoff of player 1. He went to 7, and the others remain unchanged. And this will change that the Nash equilibrium will change. So the Nash equilibrium now is as follows. So you changed the player 1 payoff, but in reality, what will change is that player 2 will play differently. So player 1 will continue to play with equal probability, and player 2 will play with probability 1/2 heads and probability 4/5 tail. And this is unintuitive, but if you do the math, this is what you obtain. Is there a problem? Because I have 8 more minutes. I have it here. So. Okay, and now is the main section of the presentation, which is LLMs play mixed strategy Nash equilibrium games. And the first question that you can ask is, does the LLM know the game? And this here you can see, for example, here is ChatGPT, and he knows very well the game. He knows what are the equilibriums. If you go to this link, you can see later that he derives all the math and everything. So he knows perfectly the game. You can do the same with Mistral, and you get the same. The emphasis is mine, but the answer is from Mistral. So he knows very well how he should play the game. But the question is, does he play the game well? And in particular, if you play a lot with ChatGPT, you will notice that he will always place head most of the time, 90% of the time or more. And in Mistral case, it's the same. So if you start playing with it, this was the user prompt. I did some small modification. This is a trick I learned from Scikit LLM, just to get one answer and not to get a very long answer. And here you get the different probabilities. So the probability of head is much higher. In Mistral case, similar, if you play with ChatGPT, is the same. It's normal because it was not trained to do that. It's not trained to randomize. But you can let the LLM run code. And this is in particular what I did before. So you can tell it, okay, but now use Python. Now you can call a function called Python. And this is what I added to the prompt. And you can see that he will perfectly. So he will know that he will need to play at random between these two choices, and he will get the right answer. And you can get the same with the Mistral. So here is what you obtain, and you obtain a nice program telling you need to play between these two options. And in particular, if you play it, it will play perfectly. So can the LLM play a small modification of the game? And this is the game I showed you before, which is I change the payoff of one of the players. In that case, if you do it even for ChatGPT, you will get that the answer is not correct. He will play at random just as before, but he will not randomize it with 1/5, 4/5. He will just continue randomizes as before. And if you do it with Mistral, so you can see the link to the full conversation. And if you do it with Mistral as well, you will get the same. So I did it programmatically so that you can repeat it, but you can get the same. So conclusions. So different conclusions. First of all, if you ask, despite the pre-existing knowledge of these classic games, so here I show you batching pennies, but you also have rock, paper, scissors in the paper, and you all basically many of these papers in which you need to randomize, and LLMs are very bad at playing these games. And you can, perhaps not surprisingly, if the internet works, just if you ask it to randomize between 1 and 10, and you ask it 1,000 times, 7 will be the most random number between 1 and 10, which is which is funny, I guess. And it's the same mistake that human does, so it's fine. 7 is the most random number between 1 and 10. And if this is one, the second is LLMs can enhance their performance if you allow them to run code. So this is, you can see this even with GPT-4 or with Mistral or with most of the LLMs. But the most important part is that there are critical limitations, which is the LLM, when confronted with games that involve a slightly more complex randomization, then it will fail it will default to be a standard scenario. So it will still go back to the standard case. So in that cases, the LLM noticeably declines, suggested that the LLMs are proficient in handling familiar games, but if you start altering the game, it will fail completely. And that's it. The case paper can be found in archive, and the code can be found here. So thank you.
Any question in your room?
Yeah, so I don't know. For the first example of function calling, for the first example of for the first example of the function calling, you describe how you can take the parameter of the function from the prompt with the LLM, and then you send this data to the Python function to generate the multiplication or the random value. Can you do the same with the for solving this problem? Like you take the information from the text to compute the information about the strategy, and you give it to a solver that will give you the number.
Yeah. I mean, I think that this can definitely be done in some way. If you think like, okay, I'm going to modify the prompt and send it in some explicit case, but it's a little bit you are tricking a little bit, no? In the sense that you would like the model to understand it. I just provide you the possibility to run any code, do it, and he should be able to deduce the math. I mean, okay, this is okay, perfect, too far-fetched, but okay. First of all, it's already a surprising result that the game is able. I mean, that the LLM is able to play perfectly in simple classic games. But if you start modifying a little bit, then the model crashes. So, but yeah, the idea will be, yeah, the model should be able to handle these kind of questions.
So you seem to have pointed out two different things, right? One, which is that the LLMs are not good at generating random numbers.
Yes.
And the other one is that they're not good at generalizing games that you've modified slightly. So, I mean, it seems that these are two very different conclusions, right? I mean, they may not even be related.
Yeah.
Right. So are they related, or are they completely, I mean, right, different?
I think that they are different. So that's why I think the paper has more than one result. I think, I mean, one result is, well, LLMs are bad at randomizing, but this perhaps is not that surprising. There is one paper which is randomization in complex continuous spaces, and they prove it for complex continuous probability distribution, etc. But here is a very simple case. It's a discrete distribution. You just need to randomize between two things. and it's still bad. So in that sense, I think that that's one result. And the second one, which is they are bad at generalizing, is also another result.
Because I mean, it seems that the random number generation, it could be simply that they don't have a good routine for generating random number. They understand the concept of random numbers, right? Because they've searched it, right? But doing it repeatedly is something that's, you need to have memory between the different things. I mean, so that I could understand. It's much harder to understand why they were not able to generalize, right? Because they've shown that they're pretty good at generalizing in a variety of other settings, right?
Yeah.
So do you have any insight as to why that's the case?
Yeah, I don't know. This is, I mean, to me, it's one limitation. I mean, there are other people trying to look at other limitations, but yeah, this is it's kind of interesting. I think also, no, it's but I don't have an answer why.
Time for last question. Yeah.
Thank you. Okay. So you show two problems. What would be your hint for a solution? So
For a solution. I mean, one trick could be what you were suggesting, which is somehow include the possible strategies within the function calling. That could be one thing. I don't have a solution for this, like in generic terms, for the second part.
Yeah, you try chat GPT like LLMs, but there is, at your knowledge, some math equivalent, because ChatGPT has been trained to do something else, not math.
Yeah.
But are you aware of some equivalent for the math world?
Yeah, I mean, there is Wizard LLM, I think it's called. And I mean, there are a lot of people trying to teach language models to do math. So it's not, which at the beginning I was a little bit skeptic, because as I was mentioning, you can run functions. So why do you want them to do arithmetic, for example, if you can already allow them to run Python code? But I think it's
for the generalization part.
Exactly. Yeah.
And did you try your problems? But did you try your
with
problems?
that one?
With that one?
No. But there is one reason also, because I wanted to use function calling, which was this.
Just to show that with a simple twist, you can solve the problem.
He can solve the problem. And in particular, Wizard doesn't have this capability. This doesn't have these particular tokens which allow them to control which tools can use.
Thank you.